Welcome back. This is the second lesson recording for IM2, October 29th, 2020. So now we're going to bring this up a notch and we're going to try to simplify 3 divided by root 2. The goal is to rewrite the expression so that the denominator does not have square root. What's the denominator? That's the bottom number, okay? Bottom number of the fraction. We do not want the square root symbol appearing as a denominator. So if you have this, the strategy we're going to use is multiplying by giant 1 made out of the square root. So in this case, what is the square root that is appearing as a denominator? It's the square root of 2. So we're going to multiply that by square root of 2 divided by square root of 2. Okay? Because square root of 2 divided by square root of 2, this is my giant 1, isn't it? Okay? Because anything divided by the same thing is giant 1. And we're allowed to multiply anything by 1 without changing its value. So that's why we're allowed to do this. And when you do this, when you multiply fractions, you always multiply across. So that's 3 multiplied by root 2 just becomes 3 root 2. And root 2 multiplied by root 2 is root 2 multiplied. So square root of 4. Square root of 4 is same as 2. So you have just gotten rid of the square root of root sign here. Okay? So 3 divided by root 2 is, or 3 over root 2 is same as 3 root 2 divided by 2. And we call this process rationalizing denominator. Okay? So you do need to take notes here. Can you take a quick note here? And then you are going to do the problems. Okay, so we're going to try to do these problems together. So what are we going to multiply to this? Okay, so here's my work. So when you have 7 over root 5, the bottom denominator radical is square root of 5. So we're going to multiply by 5, square root of 5 over square root of 5. Remember, with fractions, when you're multiplying fractions with fractions, you are multiplying top with top and bottom with bottom, and you get 7 root 5 at the top and 5 times 5 square root of 25 at the bottom, which is same as, whoops, that was a mistake, this should be 5. 7 root 5 divided by 5. B, 5 divided by root 3 is, to get rid of this square root of 3, we want to multiply by square root of 3 divided by square root of 3. You multiply across and you get 5 root 3 at the top. And then bottom, root 3 times root 3 is square root of 9, which is really the same as 3. So you get 5 root 3 divided by 3. Now C, 6 root 6 divided by root 2. You multiply by root 2 over root 2. Multiplying across, you get root 12 in the top and 2 at the bottom, because root 2 times root 2 is root 4, and which is same as 2. Now we can break the square root of 12 as square root of 4 times 3, which is square root of 4 is same as 2 multiplied by root 3, and then divide that by 2, and you know that 2 is being multiplied to root 3 and then divided, so you can cancel that out and you get root 3 as your final answer. Then E, you have 4 divided by 3 root 6. Okay, so you have 3 being multiplied to root 6. 3 is not a problem for us. It's just the root 6 that is a problem for us as a fraction at the denominator. So we're multiplying top and bottom by root 6 over root 6. And again, you're multiplying top with top, bottom with bottom, and you get 4 root 6 divided by 3 times root 6 times root 6 is just 6. So that becomes 18 at the bottom and 4 root 6 at the top. So last class you wrote these notes, okay? So you wrote the simplifying square roots. You need to be looking for perfect squares. Then you need to be looking for perfect square factors in the radicand. So for example, square root of 50 is going to become square root of 25 multiplied by 2 and so on. And then you also want to be looking for combining like roots. We're going to add yet one more thing. And you're going to write at the bottom, add to that multiply square roots. Okay, so you're multiplying square roots. And you also are going to know square roots in denominator. That means you need to rationalize the denominator by converting this into 3 root 2 over 2. So please add these two additional notes into your notebook. Alright, so why do we need to bother simplifying all these radicals? Well, it's for the sake of number sense and comparison. So if you have these radical expressions, okay, can you really compare them very well? Not really. However, when you simplify it, you are going to be able to say, okay, this is same as 14 root 6. This 5 root 54 is same as 15 root 6. And this 96 divided by root 24 is really same as 8 root 6. And that makes it really easy to compare and figure out which is the bigger number. Alright, so then we are going to revisit the Desmos exercises that we did. I do feel like I really rushed through it. So what I am going to do is I am going to ask you to go to student.desmos.com and log in with your Google account, and it should actually pull up the IM2 Unit 5 Day 1. Actually, it's the Day 1, not Day 2. And I would like you to actually just go through it one more time. Okay, just go through one more time so that we can come to these conclusions about right triangles. The right triangles have special side names. Those are legs and hypotenuse. The right angle is the largest angle and the hypotenuse is the longest side. In the Pythagorean theorem, we're going to be demonstrating that. Okay, I actually did this with the second period, but for the first period, I'm just going to do it again. Okay, so to begin, we are looking for the length of x, and we're going to leave the answer is exact form. Okay, so that means we're going to simplify radicals. So we know the Pythagorean theorem says leg, whatever the length of the leg is, squared plus the second leg length squared is going to be hypotenuse squared. So which is the leg? Leg is the two side length that is right next to the right angle symbol. Okay, so that's 8 and 12. And which is the hypotenuse? That's the side opposite the right angle. So this is the x here, which means that I can set it up as 8 squared plus 12 squared is x squared, and which is, and I can actually take a square root of both sides here, or you can do it later on. 8 squared plus 12 squared turns out to be 208, and so x is square root of 208, and which I can break down 208 as 4 times 13. And square root of 4 times square root of 4 is just 4 root 13, so x is 4 root 13. And that's our exact answer. What about this? Okay, we are dealing with radical as one of the side length. Okay, so the same thing. You do need to recognize which is hypotenuse. Hypotenuse is 8 in this case. Okay, and the legs are 5 root 2 and x. So the equation becomes x squared plus 5 root 2, and put it in parentheses and square it, is equal to 8 squared. So when you are looking at 5 root 2 squared, it's really saying 5 root 2 is being multiplied to another 5 root 2. Okay, so what does that become? That just becomes 25. 5 times 5 is 25. Root 2 times root 2 is just 2. So you get 25 multiplied by 2, which is 50. And 8 squared is 64. So you get x squared is 64 minus 50, which is 14. So x squared is 14. So taking a square root of both sides, you get x is equal to 14, square root 14. Alright, so I want you to try to do this problem yourself. Okay, please pause the video and have a look at my work and see if you can make sense out of it and if you got the right answer. And showing of work is very, very important. So make sure that you are not omitting significant steps. I don't expect you to write every single thing if it makes sense to you. However, in general, to avoid for you to make mistake, it's better to write more than less. Okay, so now let's move on to another topic. So we're going to revisit the similarity ratio. So far, we've actually matched up the corresponding side length. So in this polygon, we said that 8 and x, they are corresponding side length. So, and 6 and 72 are corresponding side length. And we've used the ratio as x over 8 is equal to 72 over 6. That's what we've said. Or you might have said 8 over x is equal to 6 over 72. Either would be fine. Okay. And then from here, you multiply both sides by 8 and you got x to be 96. Well, I am going to show you a different way now to get the same answer. Okay, in this case, what if we use the ratio within the polygon? Okay, so 6 and 8, they are the ratio within that polygon. The ratio between one of the side to this side, 6 over 8, is going to be same as 72 over x. Because, and so I can set this up as x divided by 72, x divided by 72. What does x correspond to in this other polygon? It's 8. So 8 occurs at the top, followed by divide by 6. 6 and 72 correspond, so they're the two bottom numbers. Okay. If I do the same thing and then multiply both sides by 72, you'll also get x to be 96 as well. And that's the same answer that we got previously. So it seems to work that you can use ratios. The previous one, we set it up as x over 8 divided by 70 over 60, 72 over 6, and it still worked. Okay, so it seems like the previous example, we did the interratio, or the ratio across the shape. So we compared the ratio between one shape to the other shape, so inter. But the second time we did it within the shape. So it's an intra ratio, within, inside. It's a ratio within the shape, because we are comparing the ratio of one side to the other side within the one shape that we know to be similar. This is only true when we know this, we're told or we know for sure that the two shapes are similar. So this is called intra, this is called inter, or ratio within the shape. Alright, so when two shapes are similar, the sides within the shapes are also proportional. So sometimes this is going to be helpful for us. So I would like to pause the video and take notes on this. And if you are told this, the two triangles are similar. Okay, so solve for x using within the shape same side ratio, and 2 using across the shape side ratio. Up to now we've been doing across the shape. I want you to start getting used to using the within shape. If I do that, the within shape is 104 divided by 50, 156 is going to be the question mark divided by 60. The across the shape is question mark divided by 104 is equal to 60 over 156. So I want you to start getting used to using the within shape ratio as well, because it's going to come handy for us when we are doing the sine, cosine, and tangent. And this is a quick explanation of why this works. And then I left you with this problem. Okay, and that's it for today. Thank you.